Hello, friends. We're going to talk about rolling without slipping and kinetic rotational energy in general. We have already identified, obviously, kinetic energy in a straight line is 1/2 mv squared. But it should be noted that when an object is both moving, as with a velocity, and also rotating, then that rotational energy has its own quantification of energy, 1/2 I omega squared. An object could be moving, it'll have kinetic energy due to its linear or translational motion. It could be rotating, it could have energy due to its rotation. It could be doing both of those things. And so we need to account for both of those things in its motion or in its behavior. And so when we talk about something like rolling without slipping, we've clearly got a situation where some objects are moving across a surface, and the fact that they're not slipping, that means that the surface of the ball or rotating object that's in contact with the surface that it's rolling on, those contact surfaces are stationary relative to each other. Basically, a wheel that is rolling down a road on your car, that wheel is gripping the road. If you are doing a burnout, the wheel is spinning while your car is not moving, then the surface, the contact between the wheel and the roadway is there's relative motion there, and so that would be slipping. But we're not talking about that. So the essence of rolling without slipping boils down to the fact that as an object moves along a surface, say a wheel, for example, and I will draw a line indicating 2 points on this surface and an arc length is usually given the letter S. So as the arc so I'm going to draw 2 points on this circle to represent points on the sort of give us points to identify as it rotates, and draw an arc, the arc length S, usually indicated by an S. As this wheel or whatever it is happens to roll and progresses through that arc length, when it gets to a point later where the second point is now on the ground, the wheel has traveled an arc length of S, but as a result of the fact that, sort of, if you look at it this way, this radius is connecting the contact point to the ground to the center of mass of the object, and so as it travels an arc length S, the center of mass also travels a distance S. And so the arc length S is equal to the angular displacement times the radius. And if we were to divide both of those by time, for example, well, we'd have a distance over time, that would be a velocity, divided by an angular distance over time, that would be an angular velocity. And if we were to observe a change in the linear velocity and divide that by an amount of time, and observe a change in the angular velocity and divide that by time, what we'd be solving for is the linear acceleration, and discovering that that was equal to the angular acceleration times the radius. So those relationships are ones that we will lean on heavily throughout our description of the events. And so we've got 3 objects that are rolling down. I'm only going to evaluate 2 of these objects just to show the basic idea of how the solution is considered. Well, in the case of these objects rolling down a slope, let's see, what do we know? We're told that the angle is 12 degrees and the length is 2.5 meters along the surface of the ramp. So if we've got a triangle with a length of a hypotenuse of 2.5 meters and an angle of 12 degrees, that tells us something about the height. So you might have seen this coming, since this is kinetic energy we're talking about. So conservation of energy is really going to be the dictating concept at play. So if we've got something at the top of a ramp, which is going to reach the bottom of a ramp, a concept that we should be well familiar with is the idea of conservation of energy. And in this case, well, we're starting with gravitational potential energy, and that is going to turn into, well, one part that's super obvious is kinetic energy of translation. But the new aspect, the new piece that we're adding, is the fact that because it's also rotating, there's also some rotational kinetic energy at play or at work. And so basically what we want to do is compare the different objects. Let's just do a hoop and a disc, and see if we can use that to determine how fast they're going to be going at the bottom of the ramp. Well, they've got the same mass and the same radius r, so that makes that arguably a little easier. I'm going to shrink that down. And so let's consider the fact that we've got gravitational potential energy. So we've got mg delta h. How much is it going to go down from the top to the bottom? And since we've got a triangle, we've got the delta h is the opposite side, so we've got 2.5 sine of 12 degrees. So our change in height is going to be rather inconvenient, 0.52 meters. All right. Just kind of put that there to the side. So we've got mg delta h equals, well, translational kinetic energy. It's 1/2 mv squared. Plus the rotational kinetic energy is going to be 1/2 I omega squared. So far, we haven't even distinguished what object it is that's rolling down here, but as soon as we plug in some terms for I, that's where we're essentially committing to one of these objects. Now, the hoop, the I of a hoop, is mr squared. The moment of inertia of a disk is 1/2 mr squared. So let's do a hoop first. So we'll substitute in mr squared for our value of rotational inertia in just a moment, but also the rotational velocity. Well, because the wheel is sticking to the surface, it's gripping, it's not slipping, the translational speed is directly related to its rotational speed. The faster it moves horizontally, the faster it has to spin, so that the surface sort of keeps up with the surface of the wheel. The hoop keeps up with the surface that it's moving across. And so we've got this relationship, which we just described earlier. The velocity, linear velocity, is equal to angular velocity times r. But since we're interested in how fast the objects are moving, that implies that we're looking for a velocity, a v. So having this term of omega is less convenient. So let's see if we can substitute in for omega. Well, omega equals v over r, so that can go in there. So we've got mg delta h equals 1/2 mv squared plus 1/2 the hoop mr squared times omega, which itself is v over r squared. So square both of those terms. Now, because we're talking about the hoop's radius, little r, as the hoop itself is turning. And we're talking about a hoop here. So in the moment of inertia r, we're talking about the same r. It's the hoop. We're talking about the hoop. So whether it's big R or little r, they're the same value. So r squared cancels r squared, and what we're left with is a half mv squared plus a half mv squared equals mgh, delta h. And we also have masses, which are all the same because this is all the same object we're talking about. It's the hoop. So what we've got is g delta h equals 1/2 v squared plus 1/2 v squared. So g delta h equals v squared. Square root that, and we get v equals the square root of 10 times the height, which was 0.52. So the velocity of the hoop at the bottom is going to be 2.28 meters per second. Well, the sort of good news in this analysis is that we don't have to start from scratch, because we already had an expression which kind of sets us up for the whole solution. It's just a matter of what we plug in for the object itself that's doing the rolling. So if we now plug in a different I, it's the same solution, just with a slightly tweaked value for I. So we got mg delta h equals 1/2 mv squared plus, now we're talking about the disk, so that's 1/2 of I, which itself is 1/2 mr squared, times omega squared, which still has the same relationship, v over r quantity squared, so each of those gets squared. The r's cancel, and what we've got is 1/2, I guess we can cancel the m's as well. So we've got 1/2 v squared plus 1/4 v squared equals gh. Add those together, we got 3/4 v squared equals gh. Turn that into 4/3 g h, or delta h, I keep leaving that off, but it's always there, equals v squared. Well, I guess we'll square root that, and so we got 4/3 times 10 times the height, which was 0.52, square root of all that. Is 2.63 meters per second. So we find out that by the bottom of the ramp, the disk is moving faster. So let's think about this. If we give two objects an equal distance to travel, and one of them's moving faster at the end of that distance, well, it's probably moving faster earlier in that distance as well, which basically tells us it was moving faster overall. So between the two of them, the disk is going to be the winner, which we've seen in class. We've rolled things down ramps, and we definitely saw that the disk beat the hoop. And if we were to apply the moment of inertia of a sphere, which I forget off the top of my head what its moment of inertia is, but basically repeat that, just plugging in its value for its expression for I, and we find out where the sphere comes in. Now, according to these answers, I think it comes in first, because it's got the smallest moment of inertia. So we can find a linear velocity as things roll, because as a thing rolls, you think about some of its energy sort of has to be committed to going to linear motion, but some of that energy has to sort of be committed to spinning the thing. So the higher its moment of inertia, the more energy is committed to spinning it, and the less is left over to moving it translationally. And so the higher its moment of inertia is, the slower it's going to go once it gets going. Same amount of energy is there, but it's just moving slower across your line of vision. So there's a situation where we've got both linear and rotational kinetic energy, but that's not always the case, because in that case, all of those objects were free to move. They weren't tied to any spot. They didn't have a fixed axis. They could go from here to there. And that's not always the case, as we are going to see in this very question. An object which consists of a rigid bar is hinged on the left side, and it has a point mass, or a blob at the end of it. And so we're going to let this thing go. We're going to let it fall, and we're curious about a few things. First, and the order of questions is convenient because it sort of leads us all the way through. We don't have to know how to get from here to there right off the bat. So first, let's figure out the moment of inertia of the system. Well, the thing about a moment of inertia of multiple pieces that are attached to each other is just like multiple masses attached to each other. You just add up the masses. Well, multiple moments of inertia of things attached to each other, you just add up the moments of inertia. So the moment of inertia of a bar plus the moment of inertia of a point is going to be just the sum of those two. Or I should say, the total moment of inertia will be the sum of those two. So the moment of inertia of a bar, as rotated about its end, we already know, is 1/3 ml squared, plus the point mass's moment of inertia is just a point at a distance. That's just going to be mr squared, where in this case, r is at the full length of the bar. So basically, r, its radius of movement around the axis point, is L away from the axis point. So I'll just swap that in right off the bat. All right, so our total moment of inertia is 1/3 ml squared plus ml squared. Well, that's 4/3 ml squared. Just add the two individual moments of inertia, since those two things are attached to each other and they're both rotating about the same point. Part B. Determine the location of the center of mass. Why do we need to know the center of mass? Well, let's think about an object, say like a pendulum, a perfect pendulum with a massless string. A pendulum with a massless string, as say released from horizontal, as it falls, it would fall the length of the string. And we would say that that was the height that the object fell. The thing is, with a perfect pendulum or an ideal pendulum, all of the mass is located at the end of the string. And so all of the mass fell that height. But with a distributed object, with a physical pendulum, with a thing that's really made of materials, all of the mass is not falling the entire height. Some of the mass is only falling that height. Some of the mass is only falling that height. And so how do we judge, how do we consider the height that the thing falls? The center of mass is the point that we consider for that. So if we want to describe the height of fall for a thing, we consider how far its center of mass has fallen. So for this thing, its center of mass is somewhere around there. So first we got to figure out where its center mass is along the bar. Well, let's see. We've got the bar and we've got the mass. We were told it's a bar of mass m and length L. Okay, great. And a very small object of mass m. Oh, also mass m. So that's nice. Not too complicated. All right, so it was a while ago, but the center of mass of an object is located at by this formula: x1, m1. I guess we think we did it the other way. m1 x1 plus m2 x2 over m1 plus m2. This is the general formula for the center of mass. So let's apply this. let's call M1 the bar. Now, so that's M1. Now, where is the center of mass of the bar itself? We can consider all of the mass of the bar to exist at 1/2 L. All of the mass doesn't exist at L, doesn't exist at the axis. It exists, we can consider its center mass to be right in the middle of the object itself. So that's the bar's location, plus the point mass's location, which does have a known location. So that's M, that's the same M. So it's M, and its location is L. And the total mass is 2M, because each of them is M. Add them together, we got 2M. So the center mass is going to be located at, well, let's see. So we got 1/2 ml plus ml over 2m. So that's 3/2 ml over 2m. Of course, the m's cancel. So we got 3/2 divided by 2. So that's going to be 3/4 L. That is where the center mass is located. I'm going to do that in red. 3/4 L. That is where the center mass is going to be. And now we can actually get into solving the energy part of this. So for part C, as this thing swings down from this position to here, well, we know we've got gravitational potential energy, which is going to turn into, what's it going to turn into? Might be tempted to say, oh, it's going to turn into translational kinetic energy, and it's going to turn into rotational kinetic energy. But we would be mistaken to say that because, as we talked about before, unlike a ball, it's not free to travel. This thing is locked in place by that axis, by that pivot point. So the translational kinetic energy is 0. It doesn't get to go anywhere. It doesn't get to travel. It doesn't get to translate. It can only rotate. This, I'm going to put 3 stars next to, just because that's an extremely important distinction. If the thing can move, if it can travel, then kinetic energy of translation is check, is a yes. If it cannot travel, well, if it can travel, yes, and can if it could rotate while it's doing that, then yes. However, if it's got a fixed axis, then it's got kinetic energy of rotation only. So that's a thing we need to know, because if we didn't know that, we would start throwing in extra terms and be off by quite a lot. So I think we have everything we need to know at this point, because we know we have an expression for gravitational potential energy. It's mg delta h. How far is it going to fall? Well, we found where its center mass is, and that is how we judge how far it falls. Since it started from horizontal and it falls to the vertical, then it falls a total delta h of what we had found for its center of mass, 3/4 L. So we've got an expression for gravitational potential energy. And there's no translational kinetic energy, and it's rotational kinetic energy is going to be 1/2 I omega squared. And the reason I put I in parentheses is because I'm going to make sure to sort of segregate that from the rest of the expression, because the I, as we found earlier, is not anything, it's not one of the like convenient shaped I's. It's, we had to figure that out ahead of time. So we've got that to plug in. So 1/2 of 4/3 ml squared times omega squared. So we've got mg delta h, which I guess I'll plug that in now. So delta h was 3/4 L. Now we've got a whole bunch of terms in more or less terms of each other. So let's see where we can go from here. Masses cancel. Same mass. G is there. We got an L here, and we got L squared over here. So that's going to take out one of those. So we've got G, we've got 3/4 G equals 1/2 of 4/3. So half cancels out that. So we got 2/3 L omega squared. Now we keep rearranging things. 3/2 to that side gives us 9/8 G. Just divide both sides by L. 4 by both sides by L. So that gives us 9/8 G over L equals omega squared. Square root the whole thing. Omega equals 9/8 G over L square root. It's not obvious at all. You have to do the algebra. There's no way you're going to intuit that. But it's totally doable as long as, in this case, and in many cases, we recognize a few things. One, we got a hybrid object, multiple things attached to each other. So we need to find out what its hybrid moment of inertia is. Also, we need to find out where its center of mass is, because that's how we define how far it falls. As it goes from horizontal to vertical, we measure only where the center of mass is and how far it falls. That's the change in height. And finally, we set up our conservation of energy equation and recognize whether translational kinetic energy is there or not, depending on whether the axle is free or fixed. As all these things are, it's a lot of steps, it's a lot of pieces to go together, but the best way to get better at it is practice. So let me know how you feel about it, and I'll talk to you soon. Bye.